Hello, my name is Hans Kandel, Extension Agronomist at NDSU, and I am going to share with you some information about soybean production. The first topic I would like to cover quickly is the research I've been doing on tile drainage. Tile drainage is a kind of a method to control the water table. I have a plot near Fargo, and it is divided up in 8 different pieces. It was installed commercially, and I also have control boxes to manage the water table. In the top unit, you see here where tile drainage is taking place. The soil is nicely drained. In the far end is a section of the land that was not drained, and here is on the bottom a closer look on the non-drained area. So it does work. There are some control boxes in the pictures here that are able to be set at different levels. So I'm just going to give you the overview over the last years. This is based on 20 tile drainage experiments I conducted. And at the end, you see that the two averages have a letter A and B, meaning that they are significantly different. And basically, the conclusion is that tile has a 7% higher yield than the non-tile. So tiling would be a way to manage soybean production. However, when you have tile, you usually can get into the field earlier. And on the left, you see the bars that are representing tile, and on the right, no tile. The red bar is for early planting and the green for late planting. So as soon as I could get into the field, comparing tile versus non-tile, and in that case, there is a 28% difference. So the benefit really of tiling is to get into the field earlier, and as I will discuss later, to use a later maturing cultivar as well. Another experiment that we conducted was using raised beds. We made some ridges and planted soybean on the ridges. The take-home message is that if you plant on flat land, the number of plants were lower because there was some interference of wet conditions. But of course, the bottom line is that the bushels per acre on the ridges over 6 environments was about close to 2.6 bushels higher. So again, we could manage productivity by raised beds. The next couple of slides I would like to discuss is about a benchmark project. This was a big survey that we initially did, and based on the survey, we conducted some further research. On the north end of the picture, you see that is the data collected in North Dakota. I'm only going to present the highlights, and this is showing the yield of soybeans on the Y and the yield of corn on the X. So as corn yields normally were increased, also was the yield of the soybean. So in other words, if you were able to raise better corn, you usually were also able to raise better soybeans. The next thing that we were looking is the planting date of the year. So on the bottom, it is the planting date, basically from May 1 to the May 31st. All the dots represent the average yield, which is indicated in bushels per acre for all the farmers that planted on that day. And we had observations of over 1,000 participating fields. If you look here at this regression analysis, you can see that there is a reduction taking place for each day that you are delaying in planting. So if you can plant early, and I'm talking about weather conditions should be good, soil conditions should be good, you could gain about 0.3.5 bushels per day by planting 1 day earlier. Now, one of the questions we were asking is to see what type of a maturity growers were utilizing, and this map is indicating what growers actually were using. So we see that indeed in the north we have the earlier maturing, and in the south we see that there is maturity from 1.1 to 1.4, that is in the Red River Valley area. So what I try to do is to look here at maturity groups on the bottom and yield. So because the computer is a little fuzzy, it doesn't recognize the double O's, but in this graph, the 5 represent the double O5, and the 2.5, the 25 here is a 1.5. So basically we go from a 005 all the way to a 1.5 maturity. And as you can see, again, here there is a trend that shows that there is an increased yield potential if you can change the maturity 1/10 of a point. So going from an 05 to an 06 would give you a yield potential of 0.7 bushels per acre. I'm going to talk a little bit about nodulation because we have seen that there is a lot of nitrogen in the soil samples that are recorded in this fall. And so what I would like to show you, this is an apoptic experiment. And on the left side, you see the nodules per plant. This is when no N was applied, only the rhizobia bacteria. So you can see that as the plant develops, the number of nodules also increased. The next bar here, the graph, is indicating if there was nitrogen applied to the pot at a rate of about 100 pounds. So it is either residual nitrogen or residual N given to the amount of 100 pounds per N. And you can see that definitely nitrogen will have a negative effect on the number of nodules. A big experiment that was conducted this summer was looking at nodulation, and here I'm just only presenting at the R2 stage. This is from multiple plants from multiple locations within the field. So here we are looking at different sizes. We're looking at large, which is bigger than 4 millimeters, medium 1 to 4 millimeters, and small less than 1 millimeter. And then here the nodules per plant. So in the control would have only received rhizobium bacteria. The green bar would be with 100 pounds of N. So you can kind of see that there is a significant difference in the total number of nodules as well as in the nodules that are large and small. So there are more larger. However, when you look at the size of the nodules, there is something, of course, interesting, that the nodules are like a sphere. I'm just showing you that if you have a 1 millimeter diameter nodule, that it would equal to 0.5 cubic millimeter. The formula is here. However, if you have 4 millimeters, so you have 4 times more in the diameter, but if you look at the cubic centimeters, you are way more cubic millimeter, sorry. So basically, the bigger the nodule is, the actually volume is a lot larger. So therefore, we are expressing here the large and the medium and the small, as I showed earlier, but now in cubic millimeters. And if you put those together, now the total cubic millimeters for the control per plant versus the 100 pound of L is 60% less for the control compared to the control. So nitrogen in the soil will give you a volume 60% less than the control. Of course, that also will translate into less fixation, but the plant will now utilize the nitrogen that is there. So there is less fixation, a little bit of fixation, and utilization of what is in the soil. As an example here of what happens to the yield, the control again is just with rhizobia bacteria, and then we gave only gypsum or urea 26 pounds, so not a whole lot. And then we gave nitrogen as well as sulfur. And in this case, you can see 30 pounds of N, or 26 pounds of N and 30 pounds of S gave the highest yield, but statistically they were not different. And if you start to calculate the cost of nitrogen, it would not pay to obtain that higher yield. The next section I'm going to talk about is based on work that was done by Peter Schmitz, and some of the things that we were measuring is the canopy cover as it relates to yield. So what we did, we have an app that we take a picture of the field. Here is the picture. This is now representing wheat. And then the app will calculate all the green pixels and turns them into white, and all the other pixels, which is usually the soil, into black. And then it counts all the pixels and gives it a ratio. So it will give you the ratio of the cover. So the app is used for making the pictures. So here I'm showing you the seeding rate going from 80,000 all the way to 200,000. And then the canopio is the cover from 80,000 was 56% at that late vegetative stage. And at the 200,000, it was, of course, a lot higher with 72. So it is obvious that when you make plants, there is more interception of sunlight. What also we measured was the IDC. IDC is iron chlorosis, and it is on a score of 1 to 5. The higher the number, the more chlorosis. So if you look here, with a lower seeding rate, we had higher chlorosis. The lower, with the higher seeding rate, we had lower, significantly lower IDC. The plant height also changed a little bit when we have more plants together. They compete a little bit with one another, and the plants were taller. And of course, the last thing that we are interested in is the plant heights increased, but also the bushels per acre increased. One of the parts of the study was to look at row spacing. Here I'm comparing 12-inch row spacing and 24-inch row spacing. One additional thing we did in this study is to count the emerged plants and the final stand. So the first column is what we counted just after everything was emerged, and then the final stand. We also have here a cover, and as you look at the 12-inch, there is a higher cover percent than at the 24-inch. The rows are wider, so there is less solar radiation interception. What we're interested in showing is that here the yields of the narrow row spacing is significantly higher than the wider row spacing. So the last column is looking percent loss. So if we had 12-inch row spacing, the difference between the initial versus the final stand was about 6% loss. From the 24, we had the same ratio, but if you look here at the numbers, the final stand was practically the same. But although the final stand was the same, still the bushels for the narrow row spacing were higher. Based on all these studies and the combination of all the information that we have talked about so far, I was interested in looking at planting date and then combining it with maturity and combining it with population. So we had factors an 0.5 and an 0.8 maturity, early planting as early as possible, 2 weeks later, and then we had a population of 165,000, or seeding rate, I must say, 165,000 to 185,000. Here is a field from Castleton, and if you look here between the red bars, this area was planted early and was planted later. So if I combine many of the experiments, this is over, about 9 or 10 different experiments over the 3 years. Now we're looking at the plant establishment. So the earlier you plant, the more challenging the conditions are. And we see that early planting on average had a lower stand than late planted, which was about 2 weeks earlier. So the soil warms up and we have a bit better stand. But of course, the stand is only half the picture. We want to know about the end. So maturity has a big influence in yield, as we already mentioned. However, at the end of the season, we can get frost, and that happened in 2020. So I'm going to show you here that comparing early planting with late planting. So in 2019, there was not much difference. In 2020, there was a big difference. On 2021, a slight difference, but on average, there was a significant difference in early planting, and the average was about 6.5%. So over 21 environments, 3 years, it shows that early planting is important. Now, we talked a bit about the seeding rate. Earlier, we saw that the higher seeding rate gave some higher yield. Yes, we got some higher yield, but marginally. We only got about a 1% higher yield with the seeding rate difference between 165 to 185 seeds planted. However, the interesting thing that I was looking at is the combination. So here I put all the combinations together, and the first 4 is the late maturing group. And as a group, they are definitely higher yielding as a group than the early maturing. So later maturing definitely has an advantage. When we look here at those 2 bars between the late maturing cultivar, we see that early, late, that there is a slight advantage, but although not significant, they add up together there. So if we looked here at the 185,000 versus the 165,000, you can see that numerically there was a bit of an advantage. So the advantage really of higher seeding rate is not if you average them over everything, but is especially when you plant early. And that goes together with the pictures that I already showed, where it is important to have a good initial stand. So conclusion would be to plant as early as possible, plant with a fully adapted cultivar, and using a slightly higher seeding rate. That was based on that early planting ends up with a lower stand. The next section that I would like to discuss is about fertilizing with nutrients over the top. So this is what we call prophylactic. There is no reason that there was any signs that there was any nutritional deficiency. So we just applied this one at the late vegetative stages. So we'll use several products. Then before we applied, we cut off some leaves, and then there are 2 bars here, the nutrients in part per million before application and after application. Now that application, we had it 14 days later, so there is a difference in those numbers, but the only significant number difference was between the boron. So what does it do to yield? So we have all the products here on the bottom. Control didn't receive anything. There was no significant difference between the treatments. Now, I also work together with some of my colleagues throughout the US. And if you look at 43 environments from 2019 to 2020 throughout the US, no significant difference. So the conclusion is prophylactic. When there is no issue with nutrient deficiency, there is no reason why we should apply all kinds of nutrients over the top. So if you have any questions, please let me know. You can always email me, and I thank you very much for your attention, and have a great day.